Hello.
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 I, I am
Hi.
audible. Am I audible to everyone?
Yes.
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 Okay. So we have Subaru, Isaac, and Alexina. Let's wait for 1 or 2 minutes to for others. If they join, then we can start, right? Okay. One thing more, I have not yet created the schedule for next week, 1 to 1. I'll just do it after this webinar, so you can book it after. Yes. So, anyways, I think we can start. Okay. So guys, let me share my screen first. Okay. Oh, yeah. So my screen is visible to everyone.
Yes.
Yes.
Okay. Um, friends, we have completed our first project. At least most of you have done, and now you have started on the next module. That is the deep learning one. Many of you have are in introduction to neural networks. So basically, in this module, you will mostly learn about perceptrons, softmax, maximum likelihood, entropy, gradient descent, etc. Today, we'll be talking about perceptrons, which are the basis of any neural networks. And neural network in turns are the basis of deep learning, and the applications of deep learning are tremendous. You can say it is the state of the art thing, and there is a whole bubble of deep learning here right now. In the if you talk about from career perspective, uh, like data science, you have been if is there is a boom in the IT industry about in the scope of data science and deep learning. So this nano degree has this whole module where you will be trained from theory to implementation, where you will go deep in the deep learning module and try to implement it on your own. And then we have a project 2 months later implementing image classifier. So we have like a good amount of time to complete that project. So I'll recommend all of you to complete the lessons thoroughly, understand them, and try to implement them one by one. And then in the end project would not be that difficult, it will be quite easy. So the deadline is, this module is a little longer than the previous one, so that's why we have this uh, deadline 2 months later. So apart from that, yeah, so I was talking about deep learning. So its applications are tremendous. You have self-driven cars. There's a whole nano degree about self-driven cars in Udacity. Then lots of job in that field also. Then there are fraud detections, natural language processing, which understands your text and analyze it. There are virtual assistants like Alexa and OK Google, as you use on your Google personal assistant. Then there are recommendation systems for your Netflix, which are according to your priorities. They look for the content that would be more that you would more likely to watch. They recommend you apart based on that. Then there is robotics, in which I am working. Here we mostly work on artificial intelligence and robotics, try to do some manual task without humans and make the robots intelligent enough to do it on their own. Then there is healthcare industry. So basically the scope is a lot more, but today we'll start from the one of we'll start from perceptrons, which is the unit of this whole neural network, and which in turn is the unit of whole deep learning. So let's start with perceptrons. Okay, so maybe I'll just check whether I'm recording or not. Okay, yeah, it's recording. Yeah. As you see in the screen, this is the neuron. It is the longest cell in human body, approximately 1 meter. It is the basic unit of our nervous system. You see, perceptrons were invented in 1957 on the motivation derived from this neuron cell. So as you see on the left, there are input signals from these dendrites. There are electrical signals that pass through this neuron, and in between there is chemical synapse, and through which the electronic charge is passed, and then these are output signals that is passed to next neurons. So these neurons, this one is a single unit, and together they form the whole nervous system, using which we are able to make decisions. And so this was the basic principle of perceptron. If we want to make a smart machine, we will have to have a small building unit, which when performing together will make a smart system that can perform many intelligent functions without the help of humans, right? So let's see. So this is your typical perceptron, and here are the weights associated with each input gate. You can see, let's say these are gates. Okay, so these are like 5 gates to enter this particular perceptron, and from with each gate there are weights associated with it. So everyone that tries to enter through gate has to be multiplied with that particular weight. Okay, and there is a bias in the perceptron itself. Okay, so whenever in general we try to pass it as a matrix whenever we talk about it, but you can see that these are just components. With each gate there are particular weights associated with them. Whenever an input is passed, it first get multiplied with the corresponding uh, gate weight, and then the weight, and then these are sum with the bias associated with it. So these are all different components, and you can say that in the matrix they have if we have a 2D matrix, we have component 1 and component 2. Here we have 5 dimensions and 5 weights, and 5 inputs associated with it. And the output we have is either 0 or 1. That is, this is for binary classification, that is mostly talked about in introduction to neural networks. So this is basically the perceptron, and let's dive further into that. Okay, so here we have also assigned an activation function here. It can be softmax, sigmoid, or any function. So if you see the value that it gets out from the perceptron z, it can vary. It can be a very large number, or can be a very small number based on these values. These are basically the product of these two and then sum, right? So this value could be quite large. So what if we want to? We do not want that value to explode that large. We want it in a certain range. So for that, we have certain activation functions which transform the input z to some particular value that have some ranges. Like you have sin h, you have cos h, you have tan h, which have their particular range of outputs. Similarly, we have softmax and sigmoid. They give the value between 0 to 1. So we can associate a probability with each input. So how probable it is to for a particular input to be a to assign to a particular value. Let's say we assign a threshold of zero point 0.5 and say any value which gets the a value more than zero point 0.5 is class 1, and any value which gets the active a value less than zero point 0.5 is assigned class 0. So this kind of helps in the probabilistic models as well. So that you also might have done the exercises of sigmoid and softmax functions, right? So this is my sigmoid function. You see this ranges from 0 to 1 here, and basically every value of z that comes from here is passed into this, and then the value ranges from 0 to 1. This is the basic formula of this. And so, and then there is a particular exercise which tells me in which you have to try to solve it on your own, how a sigmoid function and softmax function are same for a binary classification problem. you might want to try it out on yourself, and you will look the you will find it that they get the same kind of formula assigned. You just have to tweak the value of z in that. Okay. So I'll suggest you guys to try it on your own. If you do not if you aren't able to do it, you can personally message me. I'll just send you a photo of the proof that I have written on notebook. uh yeah, so that's pretty much about sigmoid function. It lies in this range, 0 to 1, and it helps out in assigning some probabilities to the particular outputs of the perceptron function, right? So if you say, let's say it's your birthday and you want to know whether you will get the gift or not. So probability of gift, let's say, is zero point 0.6 and probability of not gift is zero point 0.4. So based on that particular inputs, the perceptron will give you some output, and then it will pass through this activation function. And if it is more than, let's a particular threshold, let's say zero point 0.5, you will say that, yeah, I will gift the gift. I am getting the probability as zero point 0.6, so I'll probably get the gift. This is the kind of way this functions helps out the perceptron. Okay, at any moment of time, if my screen is not visible or I am not audible, please uh, give the messages on Slack or this chat window that is assigned on the YouTube, or just speak out. Maybe it happens frequently that our connections get lost. Okay, so then there is this particular exercise where you have to try to develop AND gates, OR gates, XOR gates using the logic of perceptrons. So you see, in any computer, these are the fundamental gates that are called logic gates. This for any particular operation, that is multiplication or addition or anything, the inputs are always in binary, and these are the fundamental units that help us out to perform the operation. So if you see, the inputs all are always in binary, and the outputs are also in binary. So in what happens in AND gate is, AND gate tells you it is one only if both the inputs are one. So basically it is the product of the inputs. So if 0 and 0 comes, you just multiply them and you get 0. If 0 and 1 gets, you get 0. If 1 and 0 you multiply, get 0. If 1 and 1, then you get 1. So how do we picturize it on a 2D graph and try to and solve it on through the perceptron? So what we can say is, let's say this is our y value, or the prediction, the value that we have to predict, and these are our two inputs columns, right? X and y. So on one input, we have x, we have 0, and on one input we have y. So we have to predict any value, and if that value is 0, then our prediction is correct. Now if the there are two columns, then according to the perceptron, we will have two weights, right? This typical perceptron will have two gates. Here x will be passed, and here y will be passed, and then we will predict the value of output z. Okay, so you can see that here one axis is x1 and second is x2, and here for the value of 0 0 we get the label as 0, and for value of 0 1 we get the value of 0 as evident from the table. From 1 and 0 we get 0, and from 1 and 1 we get 1. Now if we have to divide this, if we have to build a classifier, it is a linear classifier, right? Perceptron is a linear logic. It applies linear operations, so it can only get us a linear classifier. It cannot give you a curve kind of thing. It will give you a linear classifier. Also, the reason it was not accepted in 1960s was because of this limitation only, that because this cannot help us in getting some curved kind of classifiers. It is a linear classifier. So now you see this particular data set is dividable. It can be divided by a classifier of a straight line. Now our job is to find the equation of that straight line. There can be multiple straight lines from this point to this point, all parallel to this values, or maybe a little tweaked, little rotated, but do not they clearly divide these three value with this one. In case of that, if we had one here, it become quite difficult to divide us using a single line. In that case, we have different scenarios that we will discuss later. So let's see how do we find it out. So this is the solution that I tried on my notebook. So you see, w1 x1 plus w2 x2 plus b, if greater than 0, we assign the class as 1. If w1 x1 plus w2 x2 plus b, this is the output of the perceptron. If this is less than 0, that is negative, we assign the value as 0. Now we try to put all these values one by one on our perceptron. So W1 passed 0, W2 passed 0, and B is always passed 1. So these two values become 0 and B is less than 0. So that means our first conclusion is that B is negative, right? So now we pass 0 here, W1, 1 to W2, and then we find out that this much cancels out, W1, and W2 plus B is less than 0. So this is also the part of exercise that you will have to do in your module. And I am showing you the way you derive the right solution. And now 1 0 0, w1 is past 1, w2 is past 0, and b as it is, we get w1 plus b is less than 0. So you see, b is negative, w2 plus b is also negative, w1 plus b is also negative. But when we pass 1 1 and 1, we get w1 plus w2 plus b positive. That is, collectively w1 and w2 are that much positive that can balance out the negative of b, but individually they are less than 0. So let me assign the b value of -3. Here it should be -3. So if I assign it a random value that I give it -3, then w2 should be less than -3, or the mod of -3. It should be less than mod of -3. So let me assign it 2, right? So 2 minus 3 would be negative, and w1 I can also assign 2. 2 minus 3 would be negative, but w2 1 plus w2 plus b will always be positive, because 2 plus 2 minus 3 will be greater than 0, right? So here I have derived the equation of the line, or you can say the perceptron. I have found out the weights of my particular perceptron. So my weights are 2 and 2, and my bias is -3, right? So this much is clear to all of you, or is there any doubt in this? Because this exercise is quite important.
It's clear.
Okay. Yeah. So similarly, we have OR gates also. In OR gates, we have in OR gate gives us 1 whenever there is a single value is 1, right? So here in case of 0, we will get 1. In case of 0, we will get 1, because if at least one of the entry is 1, we get 1, right? So this will be 0 1 1 1. So now if we see the diagram, this particular value will be 1, this particular value will also be 1. So now the classifier will be a line through these points, in the middle of these points, right? Or any line that can divide these 3 points from this particular point. So line classifier, earlier classifier was here, now the classifier will be here. Similarly, we will do the same kind of values, but here this will change, the output will change. Here w1 0 plus w2 1 plus b would be greater than 0, because it will give out the value as 1 in case of OR gate I am speaking about. And in case of the here also, it will become greater than 0. And then solving all these 4 equations, we will get the value of OR gate also, right? uh, okay, so this is the exercise. You can try it on your own also. Now XOR gate. So let me try to explain you how was it difficult to build the XOR gate through the perceptron. So in case of XOR gate, any value in which only a single value is 1 will get the value of 1. So this will be 0 and these two will be 1, right? So let me search for an image. XOR gate perceptron. Okay, you see here, in case of OR and AND, it is quite clear and easy. But in case of XOR gate, we have values 1 in where we have as only a single input as one. So we cannot divide this data set into two classes using a single classifier line. We need more than that, right? So here they have tried to divide it through the two lines, but Perceptron can only divide it with only one line. So in these cases, what we do is we project the points in more than that, in a dimension with more degree of freedom, right? So if it is 2D, we project it into 3D space. If it is 1D, we project it into 2D space, and then we can divide the point through a plane. Let me show you how. Dividing points in 3D space projection. Okay, so there was this particular video that I saw. Okay, animation. Okay, so I'm not able to find it, but you please try to do it on YouTube. So basically, the video has these points. What it does is it project it into a 3D space. So these points, one and one, are one and one lie at different height than zero and zero. So if they lie in different height, then we can divide the projection that we get using a 2D plane. So that is also a linear classifier, and all we get it through a perceptron by dividing it, by projecting it into a higher dimension. In SVM, we also saw that we also divide that using the higher dimension, because SVM is also a linear classifier, right? And then there is this exercise where you are implementing XOR gate through these three fundamental gates. Not AND gate is also known as NAND gate. What it does is it just complements or gives the opposite of the AND gate, right? So if we are implementing XOR gate, then the output will be one if only one input is one and other input is zero. So if I pass 1 here and I pass 0 here, so 1 is from this point, 0 is from this point. So I can go to OR gate. This one gets 1 from here and 0 from here. So its output will be 1, right? Ignore the values here in between. Okay. In the middle of the perceptron, just focus on the outputs. So first one input will give me 1. Second input is giving me 0. So 1 and 0 will give me 1 from OR gate, and this one and this zero will give me zero through AND gate, but it will get NAND, it will get not. So zero will so this NAND gate will give me output one. So we have one and one from OR and NAND gate. These one and one, when passed to AND gate, will pass me the output as one. So you see, when we passed one input as one and other as zero, we get output one. Let's also try to solve it for points in which we have both 0 or both ones. So if we have 0 and 0, 0 and 0 becomes in OR gate give me output 0, and 0 and 0 in not AND gate will give me output as 1, because 0 and 0 will be 0 and 0 and will be 0, and not of 0 will give me 1. So this is 0 and this is 1. And when I AND 1 and 0, I get output 0. Similarly, for 1 and 1, when I pass 1 to the OR gate and 1 to this OR gate, it will give me OR of OR as 1, and this point will give me 0. This will give me 1 and 1, and AND of 1 and 1 will be 1, and not of AND will give me 0. So here I have 1 and here I have 0, and AND of 1 and 0 will again be 0, right? uh, so you see, first you have to implement AND gate, then you implement OR gate, then you combine them to make a XOR gate, right? Because XOR gate is not simply implementable with simple trick that we used here. Okay. These are my logic gates. These black ones are the value of 0 and the white ones are the classes of so basically two classes, 0 and 1. Black points signify correspond to 0 class, and white points class correspond to 1 class. So 0 and 0 in AND give me 0, 0 and 1 in AND give me 0, 1 and 1 in AND give me 0 and 1 in AND give me 0, and 1 and 1 will give me 1. So white class is 1. So here in OR, 0 and 0 will give me 0, 1 and 0 will give me 1. So white class is 1. 0 and 1 will be white because OR gate it will give me 1, and 1 and 1 will give me white as OR gate is 1, right? Okay. So in XOR gate, whenever we have one output, one input as 1 and other as 0, we have 1. So 0 and 1 will give me 1, and 1 and 0 will give me 1. Other than that, 0 and 0 and 1 will give me 0. So you see, these points are dividable, separable. This one is also separable, but this becomes quite difficult to separate if it is in 2D, right? Okay. Okay. And I guess it is pretty much for Perceptron. If you have any question, you can interrupt in between. Now we can go to the gradient descent part. Okay. So what happens in gradient descent is you try to minimize error by going in that particular direction, which gives you highest decrease in error, or you can say the steep is more. So if you are standing in the top of mountain, you will try to go down as fast as possible. For that, you will choose the direction that is as steep as possible. So basically, what happens in mathematics, you can say that we derive it and you go in that derivative direction, which gives you minimum fastest decrease in rate of error. So if you have 5 unit of error decrease in this direction, so for 1 unit in this direction, you get 5 unit of error decrease, and 1 unit of in 1 unit of this direction, you get 7 unit of error decrease. Then you go to this point, right? You always try to minimize it. And so if we have two parameters, theta naught and theta 1, we derive the error function on that particular direction. So what is the error rate in theta naught? Let's say it is 5. So for each unit we move into theta naught direction, our error decreases by 5 units. And for each unit we move in theta 1 direction, our error decreases by 7 units. These are hypothetical values. I'm just trying to make you understand that this is kind of speed of yours. Like, so if you have to travel 200 kilometers and you travel by 40 kilometer per hour, then you reach in 5 hours, right? So that speed helps you out in understanding how much time you need to take. So here also, how much unit of error is decreasing helps you out in finding number of steps you might take to reach your particular destination, right? So if I have 5 units of error decrease in 1 unit of here, and I multiply with alpha also, so alpha is very a small number, that helps me try to go very slow, because it might happen that there is a global minima, but I missed it because I jumped it through because of my alpha. So whatever my speed is, if my speed is 5 unit in direct direction, I multiply it with alpha. Let's say my alpha is 10 to the power minus 3. So I move in this direction x instead of 1 unit, I move in 10 to the power minus 3 unit in direction. So my error is also decreasing by 5 into 10 to the power minus 3 unit. So you understand why the derivative is significant here, because we want to understand the rate of change in a particular direction, and then we want to move ahead accordingly, right? So this is the this is the equation here. So you see theta j is my jth parameter, and in jth parameter I am changing it according to the change of my error or cost function in the direction of theta j. So whenever I derive it in on the basis of theta j, with respect to theta j, I find out the rate at which it is decreasing in direction of theta j, and then I multiply it with alpha. So I am saying that change theta j according to alpha units moved in theta j direction with respect to my cost function. So my cost function, if is it was 5 units, now with alpha 10 to the power minus 3, it will be 5 into 10 to the power minus 3, right? And I will subtract that number from theta j. So this will give me my new theta j, and this I do for all parameters. Okay, so for a single point, I let's say a single point has n parameters. So for all those n parameters, I do this thing and I update the parameters, and then I go to next point and I keep these points with me for my next point, and then update it on the basis of that point with the theta j's I got from previous point, and then I keep on doing it until my value converges or my error is so minimized that it cannot minimize further, right? That is on further going, I am moving up or my error is changing. So basically, if I go to the global or local, it may also happen that you go to local minima and up, and there is no point in going any deeper. You can always only rise higher. So at that point you say my algorithm has converged and I have got my thetas. Okay, so this is called stochastic gradient descent, where I try to do this for one particular point at a time. It is quite fast, as you can understand, but it can be a it can this jump can be quite haphazard. So for a particular point, it can move direct the theta j's to a particular direction, and that jump can be different, and so there is not a particular direction in which my algorithm is decreasing. As you see here, uh, it is very subtle. It is passing through a single pipeline kind of thing. But in stochastic gradient descent, when I try to do it for one particular point at a time, it will jump here and then here, then here, then here, then here, then here, and then it will land to the local minima. Okay. This is the implementation of stochastic gradient descent. So you are iterating in the range of you are saying let's say the algorithm converges, or you assign a maximum number of iteration till which you will do the optimization, right? So here I change my theta using theta minus alpha into gradient. So gradient is my delta j theta upon delta theta, and alpha is my uh, learning rate, or you can say the rate at which I want to run in a particular direction. So you see these there is no need of dot product, as there are no two matrices involved. Here it is a single point, right? But this can be quite slow, right? Because for each particular point we'll have to go, and then this is in calculation it is fast, but it can converge it in converging it can take a little longer. So instead of that, what we can do is we can take a bunch of points together and then run on that, right? So that can be quite longer to compute, because we have more than one points here. But it will then it will run through a subtle direction. There is no haphazard jump will be involved, and it will give me it may also converge faster. In some cases it does not, but it's okay, right? So in batch gradient descent, I dot the whole x matrix with my theta matrix, right? So this x matrix will contain all the input values, and this theta matrix will contain all my thetas, theta 1 to theta n, all the parameters that are involved. Then the whole matrix theta, here I subtract it using the np dot xt, that is transpose of x, and then I multi dot it with y hat, that is my prediction, and y that was actual values, and then I do this. So you can try to derive it on your own. If you try to this comes from this function only. If you try to derive j theta, you will understand that this will always give you this kind of function, alpha into gradient, right? And here, since it is a whole matrix, we are multiplying the matrix together, the dot product of matrix, and then there is alpha m is the my size of a batch. So if you have 100, then m is 100. So you are taking that bunch of points together. So it is this, here it is using being used as an average, right? So yeah, that's all for batch gradient descent, and this is for stochastic gradient descent. This is the simple difference. Batch gradient descent takes a whole lot of points together. So what is the practical applications here? So if you're building an image classifier, you can try to afford this stochastic gradient descent approach. You can take one point at a time. It may take longer time, but it is okay. The jump could be quite haphazard, but in the end you will converge, right? Here in batch gradient descent, let's say in robotics you are training a robot to do a particular activity. You cannot imagine it to take one point at a time to update its network, because it will be quite lengthy for that network. It needs a whole bunch of data points, and the data points could range in from millions to millions. So it can take millions of data points together as a batch exercise, and this batch size, then it will perform the gradient descent, and then it will reduce the error, right? So there are different approaches other than gradient descent also that are used to reduce the errors. But if I talk in terms of gradient descent, it will take the whole batch which has a size of millions, and whose network, whose parameters can also be in, like, say, 10 to the power 3. So if you see the DDPG algorithms and DQN algorithms, they have the powers, they have parameters in the term, in the degrees of tens, 10 to the power 2 or 3, and then there are a whole lot of image data points. No, sorry, the data points. So the matrix is 10 to the power 3 to 10 to the power 2, and this whole is passed as a batch to my gradient descent algorithm, or my whatever the algorithm they are using for optimizing. The network is updated through that, right? Okay, so this much is that. Now here you see, this red point is my optimal point. This blue point is my batch gradient descent. This green is calling me mini batch gradient descent. So batch is basically we are taking a smaller batch other than batch gradient descent, and stochastic gradient descent is this purple line. So whenever I am taking the batch, it is going through a single, not single direction, but through a the jump is quite subtle, right? So it is not jumping in this and this direction. But whenever I am increasing the size of batch. Here the size of batch is 1, but when I increase the size of batch from 1 to some, let's say some number k, then the jump is haphazard here and there. And when I do it for the batch gradient descent, the jump is even more. So you see, for 1 point it goes here, for 1 point here and there and there and there. So this is the difference between patch gradient descent and stochastic gradient descent. And you also try to derive it on your own. You take this formula, put the value of cost function, and do some calculus, derive it on basis of theta, and you will reach this particular formula only. Or for stochastic, you will reach this particular formula only. Alpha into grad, right? Gradient. So yeah, so you just need to remember this formula. This is quite easy. Or you can take the other formula, that is y minus yi uh, into gradient into alpha, y minus yi into xi into alpha. That is the formula. So that comes after deriving it. Okay. Yeah. So today we talked about gradient descent and perceptron. I guess I mostly talked in theory. Uh, so for that, you do not need to do much. The coding exercises are quite small that you can do it on your many many exercises that are there with each particular lesson, and you can try to implement it. And then there are gradient descent logic gates. You please try to do this exercise, and this one is quite good, and this one also. And right, so gradient descent, you just need to do one thing. You put the formula of cost function here, try to derive it, and then see what the formula converges to. And after that, you also see the try to do this sort of coding, right? And then see the difference in the values that thetas are giving. Just put a print theta statement out in every loop, and then you will see how the jump of thetas are here. Then you can plot it, and you will find these kind of difference between batch and stochastic gradient descent. Apart from that, I also wanted to talk to you about projects. So last week I got a good suggestion that for project I should start talking about small modules before the deadline. So I should not wait till the deadline arrives. So I should discuss it in my weekly webinars also. So I'll discuss about the next project in upcoming webinars, few segments at a time. We will keep the whole bunch of content that we are gonna cover that week, plus a small module of the project. So basically, this will motivate you to start on the project, and also help you out in case you have any confusions, so that we try to increase the number of submissions from our batch at least to this project. So if you guys do not submit your project on time, then it will eventually cause you to not being able to complete the project on time, not complete the whole nano degree on time. And then you will be able to access the content, but you will not be able to make the submissions. So that would not be something that we would like. So my job is to try to push you guys to submit the projects on time. So in the first project we did quite well, but many people have not are not responding, and may not have submitted the project. So that is a wise suggestion that I got from someone, that I should introduce the discussion of projects also in each week webinars. So this will motivate um, you people to start doing projects, and also the also will be able to submit it on time. Okay, right, let me see, I am still recording, right? Okay, so I'll just stop sharing the screen. So okay, so no doubt in today's content, was it clear?
Yes, thank you.
Okay.
Yep.
So that's all for today. This was a small session that we had today, I guess 40 odd minutes. But there was not much to discuss about perceptron and stochastic gradient descent, unless we are doing some coding. But right now, I want you to focus on the theoretical concepts, the neural networks and sort. Coding will be easier than this part. This part is more difficult than coding and implementation. After that, we will jump on the coding part as well. Okay, we'll build some MLP classify. MLP is multi-layer perceptron, and all multi-layer perceptron classifier, stacked autoencoders, and these sort of things. So we'll also talk about autoencoders. Yeah, I should give a brief about autoencoders. So autoencoders, basically, you pass the input and it extracts out important features from it, and then so basically compresses the whole input image and input data, and then it tries to expand it again to the input that was passed. So then it compares the input and output, and it should nearly match. So this kind of thing is used for image compression. As you might see that whenever you send an image through WhatsApp, it is always compressed, because they always take out the important features of the image and pass that particular image as those features. And on the receiving end, those from those particular features, the image is reconstructed. So this is also an application of deep learning. Right. Yeah, guys. So this was quite nice. To today we have covered perceptrons and gradient descent, right? So let's wrap it up today. Okay. Yeah. So you can say one by one if you have any doubts, or you can just say goodbye.
Okay, thank you. Bye.
Thank you very much.
Okay.
Thank you. Bye.
Bye. Okay. Okay, Sak, bye to you as well.